So welcome back. So now we have the live question and answer session. So let me introduce the chair of this session. So Professor Abhishek Gupta is a faculty in the Department of Electrical Engineering at IIT Kanpur, and his research interests are wireless communication. In particular, he works on stochastic geometry, and his interest also lies in molecular communication. So Abhishek, you can now compare. Yeah.
Hello, everyone, and welcome, Professor Eckford. So, in this Q&A session, we will first have, if you like, we can have a small overview from you about the lectures today, and then we can have some questions. We already have a list of questions which we have shared. We can first take that, and then we can ask if there are any other questions also.
Sure. So thank you again very much for inviting me to the entire organizing committee. It's a pleasure to speak today. I would just like to briefly highlight the basic topics of the lectures. So one thing that I would like to emphasize is my philosophy of teaching these lectures. The way in which to properly absorb the material, in my opinion, because I am using my tablet and writing notes on the tablet, I just like to emphasize that the way I think is best to interact with these lectures is for you to write the notes as I'm writing them. So I think I have a lot of experience with delivering mathematical material like this. And in my opinion, the best way to do it is to write it down yourself as I'm speaking and as I'm writing. And there's somehow that forms a connection between what you are writing and the way in which you are hearing and the way in which it's entering your memory, and that helps you understand a little better. So I'd just like to encourage you, as you're listening to these lectures, to consider getting a notebook or a tablet yourself and writing the notes as I am writing them in the lectures. So that said, I'd just like to quickly review the basic topics of the lectures. So I've divided my 8 hours into 16 roughly half-hour lectures. So there were 4 today. The first lecture, the first 2 lectures were just a brief introduction. So lecture 1 was an overview of the general area of molecular communication. Lecture 2 was some basic concepts of molecular communication. And then into lecture 3 and 4, we started talking about the mathematics and the physics. So in lecture 3, we talked about chemical reactions, mass action kinetics. These are processes that are needed in order to understand how transmitters and receivers work. And in lecture 4, we talked about the important concept of the master equation and how to understand chemical reactions as linear differential equations, with several examples given throughout. So I was given a list of questions, and we can go to those now. I guess we can start with we can see my screen now.
Yeah, I think So I think we can first take these questions, which are like we have collected.
Okay. So I'm happy to be interrupted with any new questions or requests for additional details. So just bear that in mind.
And others, if you have any questions, you can type on chat Q&A chat section, and then we can bring them one by one. So please, all the attendees, you can type your questions in the chat. Okay, thank you, Professor Eckford. Please start.
Okay, so here's the list of questions that I was just passed. I just got these about an hour ago. So from lecture 1, again, this is the first introductory lecture. Question 1, I recently read about xenobots, the first living nanomachines made from biological components. Can we use them as transmitters and receivers in molecular communication? So thank you very much for this question. I had actually never heard of xenobots until this question was asked. I very quickly looked them up. So basically what they are collections of skin and muscle cells And more or less what they do is they structures and they can move around. In principle, there's no reason at all why they can't be used as transmitters and receivers in molecular communication. But I think what you'd have to do is you would have to include in them some sort of cell that emits a molecular message. So I don't. It's unclear to me, just based on my very quick reading right now, whether that's been done yet. But I think it's certainly a promising direction to go. Question 2, how the nanomachines deployed inside a human body with some specific purpose communicate with the outside world? Okay, that's a great question. So presumably if you have a network of nanomachines inside your body, you would presumably want to control them to the outside, maybe to give them a new mission or to tell them to stop or something of that nature. So that is not something we're going to talk about very much in this series of lectures, but there is active research on it. So the paper that I'm most familiar with, I'm just going to, I just found it a second ago to remind myself. So I'm going to type it here. It's called Externally Controllable Molecular Communication. So this is a paper from 2014. I actually can't remember the journal that it was published in, but there's been quite a bit of related work since then. And basically what you do is you apply an additional layer of communication between the outside world and the molecular nanomachines. So it could be molecular, it could be radio, it could be whatever you like, but there has to be some sort of interface layer between the outside world and the molecular machines that are inside your body. So I'd encourage you to check out this paper, the papers that cite it, and that'll give you some more details on that front. Okay, lecture 2, this was again a more technical introduction to molecular communication. Now this was apparently the popular question. Apart from these bioengineering examples, it will be interesting to know what the natural molecular communication networks in the body are used for and how they accomplish their task. Okay, excellent question. However, it's extremely complicated and not fully scientifically characterized. There are many examples of communication systems within the body. And we will only, in this course, we will only touch on the very basics. And in fact, we won't even touch on human examples. So you'll see in lecture 14, I think, let's see if that's right. Yes, no, that's not the one. So in lecture 14, we're going to talk about intercellular signal transduction. And it's going to use the concepts that we talk about in lectures 3 and 4. And basically what this is, this signal transduction is one mechanism by which cells talk to each other. We're not going to talk very much about how it works inside the body because those systems tend to be complicated. We're instead going to talk about intercellular communication in different contexts, in biological but non-human contexts, because those systems are better studied. So in other words, there's better models for them. Some of these models are simpler, so they're easy to understand. But once you understand the basics of what's going on with modeling signal transduction, there's no reason in principle why you can't apply the same technique to any biological communication system, including those in the human body. So I understand that might not be a terribly satisfying answer, but I mean, biologists dedicate their entire careers to studying particular systems of communication that are used in the human body. And even these non-human biological examples are very interesting because they can perform certain tasks and they're more easy to engineer. So this is an excellent place to get started. Question 2, are there any maximum distance criteria for the receiver so that it can absorb the transmitted molecule? We're going to talk about that in a later lecture. So in later lectures, we're going to talk about free diffusion, and we're going to talk about how molecules diffuse. and how they arrive at the receiver. So the short answer is no, there's no maximum distance. But basically the issue is that the further away the receiver is, the slower the molecules arrive, the more spread out the first arrival time distribution is, and so therefore the less information you can transmit per unit time. So that'll come up in probably lecture 5, 6, 7, something like that. Is molecular communication in free space not feasible? It's very feasible. And in fact, we're going to talk about that. I'll give you a quick preview of that. The very last lecture in this series, we're going to talk about experimental approaches to molecular communication. And what we're going to talk about is systems like this one right here. So this is the first system we built in our lab. It's free space molecular communication. You can see here there's a little spray gun. Over here there's a little sensor, and we're transmitting molecular information in free space. So it's absolutely feasible to do this in free space at macro scales. We talk a lot about things like blood vessels and in-body, but that is by no means the only way in which molecular communication can be used. And in fact, I think there are plenty of interesting applications that could potentially use free space, and that'll come up in lecture 60. Question 4, do we have control over molecular emission from the transmitter, likewise in conventional wireless communication? So I understand this to ask, how precisely can we control what's happening at the transmitter? 2 ways. In the next few lectures, 5, 6, 7, and 8, we're going to talk about diffusion systems, how information can be transmitted using diffusion through Brownian motion. A common assumption that we'll make in those lectures is that the transmitter actually does have perfect control over the release times of individual molecules. So this is an assumption. One question is it a realistic assumption? In principle, yes. So we do have the technology to manipulate individual molecules and even individual atoms. You may have heard of a device called the atomic force microscope. You can actually pick up individual atoms or molecules and move them around. So there's no reason in principle why we can't have perfect control over molecules released at the transmitter. In practice, it's much less controlled than that. So that experimental system I just showed you, obviously emitting a spray of vapor, is much less controlled than manipulating individual molecules. So in other words, basically releasing a cloud of solvent and solute is much less controlled than controlling exactly where the individual molecules are at any given time. In biological examples, basically what will happen is you have ion channels. So you will have a reservoir of ions on one side, a cell boundary, and then free space on the other side. And what the cell will do in order to send a signal is it will open channels on the cell boundary, allowing ions to escape. So it's a little more controlled, but it's a little less. It's also less than controlling exactly where individual molecules go. Nonetheless, we use the assumption of perfect control because it's mathematically very clean. Question 5. In a practical molecular communication system, how will the receiver count the number of molecules? Great question. So again, in principle, there's no reason why it can't count the number of molecules. What you could do is, so there are things that we're going to talk about called receptors. I think we talk a little bit about them in lecture 4, in lecture 3 or 4. So what you could do is you could have some sort of sensor that detects when a receptor is occupied and simply take account of that. There are other ways to do it as well. So you could have some very precise laser system or something like that, some sort of light system that that causes atoms to fluoresce, and you could count the number. So there are ways to do this. Again, it's probably not the most practical way to design a molecular communication system. What we're going to do in practice is we're going to design systems that are sensitive to the concentration. So the concentration, as we'll argue later, the concentration is equivalent to the count. So I mean, as the count goes up, the concentration goes up, and vice versa. So what we're going to find is that if you can design a system that's sensitive to the concentration, then that gives you at least a noisy measure of the count of the number of molecules. So when we deal with exact count, our interest is in designing models that can be solved explicitly and that abstract away any difficulties so that we can add them back later as noise. So when we talk about counts and we say that we can give an exact count, obviously that's not the most practical thing that we can do, but it gives us an idea of how to solve the problem for concentration. Okay, moving on to lecture 3. So in lecture 3, we were talking.
Andrew, there's a question from Suman Ghosh, so maybe you want to answer that. There's a question from Suman Ghosh. He raised his hand.
Yes, go ahead, please.
Hello, Andrew. Can you hear me? Hello.
I can hear you. There's a bit of noise though.
Okay. So I just wanted to know about the rate matrix, that is R. Okay, that you defined in at the end of the lecture 2. So shouldn't be the diagonal entries of the rate matrix is at 0? Like you kept it minus k plus and minus k minus, but like dA of dt is dependent on k plus of concentration of B, and dB of dt is actually dependent on k minus of A, concentration of A. So that so the cross diagonal, so diagonal entries should be 0, right? Can you please explain that one?
Yeah, the diagonal entries. Let me see if I can find it here. Okay, here's an example of an R matrix. So the idea here is that the columns have to sum to 0, and that's because an individual molecule or an individual. So this specific example has to do with a forward-backward reaction involving a single species that goes from state A to state B. So each individual molecule here can be in either A or B. What that means is that if I take some A and put them in B, then that occurs at this rate K plus. So B increases in that example. So in other words, I take some A's and I put them in B, and so B increases, but A must decrease by the same amount. So these columns have to sum to 0 in order to express that balance. So it's basically a way of keeping account over how many molecules are transformed from one to the other. And if you go in one direction, so in other words, you take some A and turn it into B, then B goes up, but A has to go down. And that's why these columns have to sum to 0.
Okay.
Does that make sense?
So if you the equation, that is dB concentration of B dt equal to K plus of concentration of A. So there should be some K like minus K plus of B, right?
So if I look at this specific equation, if I take the second row here of the rate matrix, I multiply that by here. So the increase in A, is given by K plus A. So that expresses this forward reaction from A to B. So in other words, some fraction K plus of A ends up in B, and that'll end up in the second row here. However, the same amount must exit A. So in other words, in the first row, I decrease the new value of A by minus K plus.
Okay.
So in the first row, I decrease it by minus K plus. In the second row, I increase it by K plus. So there has to be that balance, because if I turn A into B, then B must increase by the same amount that A decreases. Okay, I think I see that that question asker has gone, so I assume we answered the question satisfactorily. So we'll move on.
Yes.
All right, lecture 3. How are we doing on time? Oh, we got about 10 minutes. Lecture 3, question 1. In comparison with the previous slides, can we say that there are 2 transmitters simultaneously emitting type A and type B, and they're combined at the receiver end? Okay, so I assume that the question asker is asking about this reaction, A plus B reacting to AB. Okay, so that is one possible interpretation of what's going on here, but the probably the interpretation that I like to think about is that A is the signal and B is the receiver. So B is a protein that's waiting at the receiver to interact with A. A comes along and hits B, and then they form this complex, which is the receiver attached to A. So in other words, B is just sitting at the receiver, A comes along, interacts with it, and once we form AB, then that is the complex that represents the received molecule. Now, of course, this is a reaction. Most reactions are reversible, so AB can potentially dissociate into AB, or could potentially dissociate into just A, and then some byproduct that represents a degraded B. But probably the right way to think about it, like I say, is that A is the signal, B is the receiver. So if B is just by itself, then it's empty. And if it forms AB, then it has received the molecule. Question 2, under what assumptions a molecular communication system can be considered as linear? Well, you can see for yourself here in this particular set of reactions that the master equation is expressed by a linear differential equation. So under we talked about I think in this lecture we talked about mass action kinetics. If you can take the chemical equation and write down a linear master equation, then it's linear. Now it'll sometimes happen that it's not linear. In fact, it will very often happen that it's not linear. All the examples I'm going to give you are linear because they're easy to deal with one exception. When we talked about McKellis-Minton kinetics, that's actually nonlinear, so that's an example of a nonlinear system. But if you form complexes like, if you have a chemical equation like this, if every unit, if every element of the chemical equation has a multiplicity of 1, so there's 1A and 1B forming 1AB, then it's I don't want to say it's always linear. Maybe there's some example where it's not, but that's usually the case. That will be linear. If you have a 2 here, if it's A plus 2B or something like that, then it turns out that under mass action kinetics, you will end up with the rate being given by the concentration of A times the concentration of B squared. So whatever number here, that's the exponent here, and then it will no longer be linear. And that is a much more difficult situation to handle. Question 3, is molecular communication systems time variant or invariant? Interesting question. We normally assume that they are time invariant simply because like in radio communications, time variant systems are much harder to deal with. So we just kind of assume that it's time invariant. But there's no reason why it wouldn't be time variant. So for example, you could have, so if you're using concentration of signal and the concentration is changing with time, then it's naturally time varying. But if we're talking about the nature of the channel being time variant or invariant, then I guess the question you'd have is, are these reaction rates time varying? So these reaction rates can depend on things like diffusion coefficient, temperature, pressure, all kinds of things that could potentially be time varying. You could see a time variance being introduced through the rate matrix. Okay, moving on to lecture 4. How would the R matrix change if the reaction is not reversible? Interesting question. So is this lecture 4? Yeah. Actually, it's probably better if I look at lecture 3 here. So here's an example of a reversible chemical reaction where I can go from A to B and B to A. And I also had the same example up here, A to B, and A to B makes AB, and AB dissociates to A plus B. If this wasn't reversible, so you can imagine A goes to B, if B goes to A, that rate is 0, then basically all of the K minus entries would be 0. So what we would end up with is a degenerate matrix. We'd have K plus, minus K plus, 0, and 0. Now, it's not always the case. I mean, a situation where you have two species like this, where it's not reversible, this is kind of trivial because eventually all the A will be transformed into B, and that's the end. There's nothing else that can happen. But you can have an example of 3. So for instance, if you had A, B, and C, you can basically go around the ring and none of those need to be reversible, and that's fine. So you could have A to B, B to C, C to A. So a lot of these entries would just be 0. There's a specific example of that. I can't remember if I don't think I talked about that in these lectures, but I've written a paper about a receptor called channel rhodopsin that does exactly that. So you have A, B, C, and it goes around in a ring. Now, in practice, thermodynamically, basically every reaction is reversible. However, sometimes some of these rates are so small that you can ignore them. So that's the case in channel rhodopsin. Lecture 4, should not the diagonal entries of R are 0? I think we just dealt with that question, so I'll skip over that. So in steady state, neither A transform into B nor B into A. When does it occur in molecular communication? Okay, I think I understand the question. So let's take a look. Right. So we talked about steady state here, and basically what we said was that there's a steady state solution where the dy by dt is 0. So the correct interpretation there is, in fact, that nothing's happening, but rather the rate at which A is still reacting to B and B is still reacting to A, but they do so such that these concentrations stay constant. So in other words, the rate at which A goes to B and the rate at which B goes to A balance out. So there's no net change. When does this occur? It actually occurs in the following way. So in signal transduction, when we get there, we'll see that some of these rates are actually dependent on the concentration of something else. So for instance, there's like a fuel or something like that. So what you can do is you can modify these rates to change the steady state concentration. So in other words, let's suppose you use a certain chemical to communicate, which changes these rates, but you're only allowed to measure these rates or these concentrations. So if you modify those concentrations and wait a while, it'll push it into a different steady state. Then you can measure this and figure out what bit was sent or what message was sent. So that's a specific example of how that might work. Question 4, is there any range for steady state ratio? I can't think of any off the top of my head. I mean, it depends on the system. So what you'll see is that these rates will be published for various systems, and like basically you can go to the literature and look them up for whatever system you're interested in. I don't necessarily want to come up with anything off the top of my head, but I mean, it won't be ridiculous. It'll be probably within, a factor of 100 or so, or less. Question 5, can we use McKellis-Menten kinetics to solve ligand receptor problems in the receiver? Short answer is yes, you can, but in a different way to how we're going to solve it later on in lecture 14. So this is actually, as you can see, it ends up being a nonlinear set of equations because both E and S are changing. So this process, going from E and S separately to E and S together, this is similar to reception of a signal and signal transduction. And then this additional step of producing a product, this is similar to a process that we're actually not going to talk about very much, which is how the signal transduction signal is used by the cell. And this, what happens there, the process is called the second messenger. So basically, this complex is formed, and then the cell goes on and produces second messengers, which actually carry out the task implied by the signal. So this is an example of showing how such a process might be carried out. We're going to use a much simplified way of thinking about this that only looks at the linear part, just basically assuming the concentration of receptors here, which play the part of the enzyme, assuming that is constant, and basically then we just go from S to ES like that. So that's all the questions I have here. I see we're just about out of time. There's a question or two. I see there's one over on, there's one over on the Q&A.
Yeah, hi, Udit. Can you ask your question?
Hello, sir. Sir, in organic reactions, it is very common for kinetics to follow a non-integer order. So are there any interesting properties apart from the constant phase effect, which over a wide frequency range, which comes into play? Because in electronic circuits, we usually have integer order inductors and capacitors, where the differential equation, the order just comes down to an integer. So one property which I am aware of is that fractional order kinetics, they give off the same phase difference for a wide range of frequencies. But are there any other interesting properties which show up in such cases?
It's an interesting question, and I have to admit it's not something that I've thought a lot about. Yeah, I have to be honest. I have not studied that, but it's an interesting question. As far as I know, it would be an open research question as far as what effect that would have on these kinds of reaction systems. So that's, thank you for that. Unfortunately, I don't have an answer for you, but as far as I know, that's open.
Okay, so it's about time. So we just will take a quick snap. Okay, I'll just invite the students who have asked questions, and they can open this thing.
Meanwhile, does any participant has any other questions?
Okay, so whoever is taking picture, Andrew, you look this side. Yeah, okay. Okay, thank you. You may see this in your IT newsletter. I don't know. Okay, thanks, Andrew. Thanks, Abhishek. So, let's thank Andrew again. Okay.
Thank you, sir.
Thanks, everyone. Okay. I'll see you tomorrow.
Bye. Yeah. So I requested Harpreet to come a little earlier because he also had we also received lots of questions for him. So what I will do is I will wait for basically him to come we will go to the networking launch, and the moment he comes, I'll bring you all to the auditorium. Okay, so the next session supposed to start at 7, may start early at 6:55 or so. Okay, thank you.